Let's take another look at hexadecimal numbers. To do that, we'll start with a quick review of decimal, base 10 numbers that we've all grown up with. We're going to use what we know about base 10, our comfort zone number system, and extend that knowledge to base 16, our not-so-comfort zone number system. It's called base 10 because it uses 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And it's laid out like this, with each digit or column having a place value. We know all of these place values because we've been taught since we were kids. We don't stop to think that each place value is just a power of the base. That is, 10 raised to some power. That means... So what does a number like 25,839 really mean? It means you multiply each digit in the number times its place value. So you'd multiply 2 times 10,000, then multiply 5 times 1,000, and so on. Then add them all up. And you get the answer, 25,839. And you go, well, duh, Ladley, wasn't that pretty obvious from the start? And the answer is yes, but only because you're so used to base 10 that you don't even have to think about it. Where it becomes foreign is when the base changes to something like, base 16. Then you have to think about it. It's called base 16 because there are 16 digits, not 10. But once we use up the digits 0 through 9 that we've grown to love, how do we get 6 more digits? One guess would be that Moses came down from the mountain and... Nah, that probably isn't it. Okay, somebody just decided, hey, let's use some letters for the other 6. So remembering that each of these is one digit in hex, here they are. In this scheme, A stands for 10, B stands for 11, C for 12, D for 13, E for 14, and F for 15. And the capitalization of the letters doesn't matter. Here's what it looks like with place values. And you go, what? Where did those come from? And the answer is, the pattern in hex is just what it is in base 10. There's just more digits. That means each place value is a power of 16, not 10. Again, how we get the place values is just powers of 16, and we can put any of the 16 digits 0 through F into each place. So what does a number like B7E4 mean in hex? Well, it means you do just what you did in base 10. That is, you multiply each digit in the number times its place value. So we multiply B times 4,096, but you have to remember B is really 11. So it's 11 times 4,096. Then 7 times 256, then E times 16, which really means 14 times 16, and finally 4 times 1. When you add them all up, you get 47,076 in decimal. Something else. In hex, every 2 digits is a byte. And remember, a byte is 8 bits. So this example represents a 16-bit number. So what's the largest unsigned 16-bit value you could have? Remember, that size is called a word in assembly. To get the largest, we'd have to put the digit F in each place value, like this. That means 15 times 4,096, 15 times 256, 15 times 16, and 15 times 1. And then you add them all together. The total is 65,535, or 2 raised to the 16th power minus 1. So why would anybody in their right mind invent something like hex? And the answer is, it's a really compact way of writing binary. Look at this 16-bit binary number. Now let's split that number into groups of 4 bits, and 4 bits is called a nibble, by the way. I'm not kidding, because it's half a byte. Hey, I didn't make it up. Look at the most significant 4 bits, 1011. In binary, that's 8 plus 2 plus 1, 11. And in hex, 11 is B, so that first 4 bits could be written B. The next 4 bits is 0111, which is binary 7. It's the same in hex. The next 4 bits, 1110, is 14. In hex, that's E. And finally, the least significant 4 bits is 0100, which is 4. If you go back a little bit in this video, the hex number B7E4 was an example of how a hex works. Its value is 47,076. Notice that in binary, this number takes 16 digits, the ones and the O's. In base 10, it takes 5, but in hex, it only takes 4. And as numbers get larger, this compacting effect of hex to express really big numbers, it's even more evident. Remember, we're going to be working with 32-bit numbers. What's the largest unsigned integer we could store in 32 bits? According to the text, it would be 2 raised to the 32nd power minus 1. That's 4,294,000 and some other numbers in there. That number takes 32 digits in binary, 10 digits in base 10, but only 8 digits in hex. So to wrap this video up, if we're talking about signed 32-bit values, the largest positive would be 2 raised to the 31st power minus 1, or a little over 2 billion. And the smallest negative number would be the negative of 2 raised to the 31st power, or negative 2 billion and something. Do y'all remember in C or C++ or Java, when you were learning the range for ints? It looked like this. Why? Because ints are stored in 32-bit fashion in those languages. That wraps this one up. I hope it helps.